Good afternoon. My name is Jeff Thorson. I'm the Associate Director for TIZET, the Trottier Institute for Sustainability in Engineering and Design. Before we start, I'd like to acknowledge that McGill University is located on land which has long served as a site of meeting and exchange amongst Indigenous peoples. We acknowledge and thank the diverse peoples whose presence marks this territory on which peoples of the world now gather. Welcome everyone to our SED180 event, which is the last phase of the fall SEDTalks training program. Before we get started, I want to let everyone know of today's agenda. First, we'll have my opening remarks, and then we'll move to the student presentations where each student will give their 3-minute talk about their research. After that, I'll introduce the selection committee, or the judges of our program this year, and then we'll announce the 2022 ChangeMakers. Throughout the talks, you'll be able to vote on the Audience Choice Award. You can see the link to the poll below. It'll be open throughout the talk, so please feel free to vote at any time for your preferred speaker. For those who don't know much about the SEDTalks training program, we created SEDTalks back in 2016. And this program was initially inspired by a lecture series that I participated in as a graduate student at Caltech, just some years ago now, that acknowledged excellence in graduate student research. The program was run by students and organized, and the student selection committee selected awardees and worked with them to communicate their research to a broad audience of students, faculty, and the general public. Having seen that this could be successful even with an extremely mathematical PhD on string theory, it was clear to me that we at TIZET could do the same, drawing on our excellent pool of students working on areas of sustainability and engineering and design that are of critical importance to our society. Over the years, TIZET has partnered with McGill's Skill Sets program to develop a series of workshops, complete with small group feedback sessions and individual coaching. Today, you'll hear talks from graduate students from across our faculty, each of whom have gone through over 10 hours of training on how to prepare their 3-minute talks. From among these presenters, a selection committee will choose these 3 students to be our 2022 ChangeMakers, who will then proceed to the winter training program and give their full TED Talk style presentations at our annual SEDTalks event in March. Since 2016, over 80 graduate students have participated in the training program and 15 ChangeMakers have given their SEDTalks. And I'm happy to say that over the course of those 6 years, the students that went through the training have remained involved, have volunteered their time and expertise to help coach the next cohorts of students. One example of this is our MC for today, Mr. Yue Fung. Yue is a graduate student in the faculty who took part in the program and was one of our ChangeMakers back in 2019. I'd like to now turn things over to him. Enjoy the talks, everyone. Yue.
Thank you, Professor Bertelsen, for the introduction, and I'm happy to be here together with everyone as we conclude the SEDTalks fall training with the SED180 event. I have been having the pleasure to work with the students and practice with them and coaching them throughout the training for this semester, together with Dr. Andrew Churchill here today. And it's really remarkable to be here today to witness the fruit of their labor. Today, you will have 10 presenters presenting their research, and you will be hearing presentations about innovative ways we can address sustainability issues that our society faces. All of this impressive research encompasses several fields of studies, including food security, how to decarbonize our electric grids, and also how to mine in a more sustainable way. Without further ado, I will really introduce our first presenter, Phil Cimento, who is a PhD candidate in chemical engineering. His presentation will be food security via carbon-free atmospheric nitrogen utilization. Thank you.
You may be aware the way we produce food is not sustainable. What you may not be aware of is that 26% of all global greenhouse gas emissions that we release are related to our agricultural sector. What you also may not be aware about is 10% of those global greenhouse gas emissions come from the production of synthesized fertilizers. Now, what if we got rid of these synthesized fertilizers? How much food would we lose on this plate of food? 10%? 20%? 30%? 50% of all food that we produce today comes from synthetic fertilizers. Now, these synthetic fertilizers are important, and we can't just get rid of them. But what we need is a sustainable, carbon-free way of producing these fertilizers so that we can guarantee that 10 to 20 years, to 50 years, to 100 years down the line, our kids have a full plate of food. So where's the problem? The problem is with the nitrogen molecule. This molecule is extremely stable due to the triple bond of the nitrogen molecule. It requires a large amount of energy to dissociate, and the usefulness of nitrogen is in its monatomic state. So what's the good part? The good part is that we have plenty of nitrogen. Nitrogen actually makes up to 80% of our atmosphere, with the other 20% being oxygen. So the question that we have is, how can we take this readily available resource and turn it into something useful, something organic, some type of fertilizers? The way we have to do it in our lab is a very energy efficient manner through plasmas. In order for us to perform plasma chemistry, we excite electrons readily available in our atmosphere. And these electrons transfer energy inside collisions with heavier molecules. When these molecules collide with these electrons, they can vibrate, they can rotate, or they can translate. But the most useful form of energy transfer we can have with a collision between an electron and a molecule is the weakening of this triple bond inside a metastable state of nitrogen. From here, we can take this molecule and we can react it through other methods, such as catalytic methods or other type of chemical methods. Now, what does this look like in practice? On the left, I have a picture of a plasma reactor inside our lab. It's very shiny, it's very bright, but what's inside this little sample is a bunch of super excited and radical species that we can use in order to form further products. The way we form this is typically very simple. What we do is we apply some type of electric potential across this gas. And this electric potential can come from renewable sources, such as wind, solar, hydro. It doesn't matter. But here is our bridge in order to forming an energy-efficient manner to produce synthetic fertilizers. So here's our connection. We can take our nitrogen molecules and produce organic materials, and these organic materials can formally make food. Thank you.
So thank you, Phil Cimento, for the very interesting presentation on how we can enjoy our food without worrying about the sustainability issues that might be caused. Next up, we have Shashini Rathnayaka. She is a Master of Science candidate in Chemical Engineering. Her presentation will be on sustainable manufacturing of air transports.
We all know air traveling has concerns over environmental impact because it has high carbon emission. Similarly, even the manufacturing itself of airplanes has raised concerns because it has a very unsustainable manufacturing process. Let me explain one such problem I am trying to solve. Most of the parts in the airplane structure is made up of composites. Composites are basically two or more materials combined together in order to have superior performance. You can see in the image there are fibers impregnated in a resin material. So how do they make these airplane parts using composites? They use molds. They put the composite material inside the mold and get the shape and bake it. But there's a problem. They have to use a release coating in between the composite and the mold in order to prevent from these composites to adhere onto the mold, because otherwise it is harder to remove it from the mold. So kind of the similar situation as we use grease when we are baking a cake. So these release coatings are usually sprayable solutions with volatile organic compounds, which contributes to the environmental greenhouse effect. And also, since these are aerosols, they contaminate air and causes health issues to the workers, and also contaminate the airplane part itself. So how do we solve this issue? We looked at nature. We know on the lotus leaf, water cannot retain and it also easily. That is because of the micro and nanoscale features that are present on the lotus leaf. These micro and nanoscale features can trap air in between the structure and prevent water penetration into the cavities and reduce the solid to liquid contact area. Similarly, I am trying to reduce the solid to composite to mold contact area by introducing micro and nanoscale features onto the mold surface. For that, I am using high-speed laser micromachining, as you can see in the image. So, by changing the laser intensity and the scanning speed, I can change the micro and nano features that are introduced to the mold surface, and also by changing the lasing environment, I can change the surface chemistry of the mold surface to have weaker bonding forces with the composite. So, by changing those two parameters, I am trying to reduce the composite adhesion onto a mold surface. Thank you.
Thank you, Shashini, Rathnayaka, for a very interesting presentation as we learn from nature how to do things right to help save the nature. And next up, we have Zahra Rahmani. She's a PhD candidate in civil engineering and applied mechanics. The presentation is titled Copper in Drinking Water. Thank you.
Hello, everybody, and welcome to my presentation, which is about copper in drinking water. Our body has three main sources of copper, which is our food, our drinking water, and some supplements that some people are taking on a daily basis, which itself give us about 2 milligrams per liter of copper. Almost all of us think that copper is good for our body, and but now I want to say that it could be toxic even at standard levels. And it could make some disease, which is very common in this century, especially in developed countries such as Canada, and it could make Alzheimer. And we have to think more about copper. And our project has different steps. First steps goes back to schools. So why schools? Because we think that children are so sensitive, especially for toxic materials. So it's very important to think about children at first. So we are going to select 50 schools in Montreal and then gather a lot of samples in different tabs to determine the level of copper. And after that, we are considering the effect of a lot of variables, such as pH, temperature, the age of building, the material of plumbing, which is usually copper, especially in old buildings. And after that, next step goes back to reassessing copper guidelines. In Canada now, we are just following WHO's guideline, which is 2 ppm. But we think that we have to reassess this guideline because there is insufficient data and questionable interpretation, and also high uncertainty about this number. So we have to think more about these parameters. After that, next step could be suggesting a way, so what we have to do something for removing or decreasing the copper level. For this step, we are going to use scallop shells because they are very common in different countries worldwide. So we are going to suggest a magic combination of scallop shells waste, and we are going to add these scallop shells to starch, which is so accessible, easy to access, and on the other hand, it's cheap, and add it to clay. And we are thinking about multimolinate, which is very common, and in different countries we could have good access to multimolinate and add together in different ratios, then find a good and cost-benefit combination of these three materials, then find a good ratio, and after that we could go for it and remove copper from drinking water. That was all of my presentation. Thank you.
Thank you, Zahra Rahmani. That was a really good research that helped us to drink water safely and also save the environment. by not wasting the waters. Next up, we have Valerie Lamenta, who is a Master of Science candidate in Mechanical Engineering. Her presentation will be on utilizing inexpensive materials in the clean energy transition, molten salt experimentation.
Hi, everyone. So, what if I told you that the solution to inexpensive energy storage, more efficient solar power, and safer nuclear was directly on your dinner table? That's right. I'm referring to the salt inside that shaker. More specifically, I'll be talking about molten salt. So we're all used to seeing salt in this regular granulated solid form. However, once salt is heated above 250 degrees Celsius, going to 500 or even above 1,000 degrees Celsius, it becomes molten. And in this liquid state, salt is able to store a lot of heat, and it does so at ambient pressure. And this is a very critical detail for a lot of power generation and industrial applications, which typically rely on highly pressurized steam. So, what's the problem? Well, we don't fully understand how heat is being stored and transferred within the molten salt. So that means that current systems using molten salt have a lot of redundant safety features, a lot of constraints, and this leads to non-competitive higher costs. In other words, we're taking an inexpensive resource and we're turning it into a costly technology. Well, this is where my research comes in. My goal is to apply an experimental technique directly on molten salts in order to visualize how they move as heat is being stored. The technique is called particle image velocimetry, or PIV for short. It entails seeding the salt with very small particles that follow the flow. Then a laser light is shown down into the salt, illuminating those particles. And finally, through a series of very fast images, we're able to detect how the salt moves by the light that's being reflected by the particles. This is not a new experimental technique, but it's never been applied to molten salt directly. And what you see behind me are actually some of my preliminary results showing PIV being done directly on the molten salts, and all of this is happening at 500 degrees Celsius. So what now? What do we do with all of this data? Well, current molten salt simulations actually rely on inexact experimental data. Therefore, my results will offer an accurate foundation to test and validate current and future molten salt system, all the while taking into account their extreme operating conditions. Therefore, this will lead to inexpensive, safer, and more efficient real-world systems. Finally, I believe that this research is not only applicable to heat transfer engineers and experimentalists, but I truly believe and I'm confident that this will help further innovation utilizing inexpensive materials such as molten salt in the clean energy transition. Thank you.
Thank you, Valerie, for the very interesting presentation. It's so eye-opening to know that what we have in our home can be the potential solution to sustainable energy storage. And next up, we have Junyuan Zhao, who is a PhD candidate in the Department of Electrical and Computer Engineering. Her presentation is on power balance in community microgrids.
Have you ever been in a power outage? It's dark and cold. People line up for water and food. And it's a disaster for those who need medical equipment to survive. These pictures show the Texas power outage just happened this year. Even if the main grids are so sophisticated, sometimes they still can fail. If it happens, does that mean we can do nothing about it? Of course not. We have community microgrids. But in practice, even if we have enough capacity, sometimes power balance still can't be met. In such cases, load shedding happens, which means the operator would cut off power supply somewhere. Why would this happen? Let's imagine you are a microgrid operator. It's a sunny day, the wind blows, and the household loads are low. So you have enough solar and wind power to supply your demand, and you can even store them in batteries. You look at the diesel generators, they're still on. What would you do? turn them off, right? Because the optimization software says that'll minimize costs. But at the next time step, it's cloudy, there's no wind, and there's a drastic increase in electric vehicle charging. So you have to use the energy stored in the batteries. As you're hurrying up to start up the generators, which takes time, the batteries run out. So you have to cut out some load. It shouldn't have happened, right? And this is our solution. What if I thought of uncertainty before? It's all about the horizon. Let's say my system allows me to make decisions every 5 minutes. Now, every time I look ahead and predict an envelope that covers uncertainty in the next 1 hour, and based on that, I make decisions for these 5 minutes, and I repeat the process. So the dilemma we just talked about would less likely happen. Let's make it even better. In the past, we accumulated many historical data in operation. We can use data-driven methods to replace optimization software. That'll be faster, cheaper, and easier to implement in hardware. And data enables us to capture uncertainty better, to reduce load shedding further. And now we can balance our generation and demand better and provide more security to our community microgrids. Thanks for your attention.
Thank you, Junyuan, for the impressive research, such that we can see what we do here can impact the different communities all around the world in energy storage and balance. Next up, we have Anirban Kundu. He's a PhD candidate in civil engineering and applied mechanics. His presentation will be on bacterial hide-and-seek to clean oil spills. Thank you.
A lot of you may have seen this bird. But this bird is pretty famous, considering that it has been rescued from the worst oil spill in US history. Now that's just one case. What if I told you Canada had 2,000 plus oil contaminated sites? Now, as environmental engineers, we need to have solutions to these problems, and luckily, we have physical, chemical, and biological methods. The problem is, physical and chemical methods are worse than the spill. They are adverse, and they have a lot of bad impacts on the soil and the community. Biological methods, on the other hand, are sustainable because we are using the indigenous microbes to degrade the oil, right? Well, they only work 30% of the time. And that is where my research comes in. Utilizing the principles of microbiology and geochemistry, how can we go from 30 to say 70% efficiency? In the lab, how I start this work is by considering different soils from Canada, and I mimic the fuel spill as it happens on the site. Over time, I monitor the cleanup levels, and I also monitor the bacteria as they emerge over time. Most importantly, I study the very small bacterial habitats using geochemical methods and image analysis. And what I see is very interesting. You see, in some soils, the pore structure of the soil is such that the oil and the bacteria are free to move about. There is a lot of mobility, which is why there is a lot of accessibility between the bacteria and the oil. What you get is very good cleanups. Whereas in some soils, the oils are hidden in very small locations, sub-micron scale, which the bacteria cannot access due to size constraints. These soils have very low cleanups. Thus, what my research tells or advises or helps the site remediation industry is evaluate these scenarios first, the bioaccessibility scenario, before proceeding with lengthy, costly site cleanups. Thank you.
Thank you, Anirban, for the interesting presentation, how we can use biological methods to save the poor animals that are victims of oil spills. Before I introduce the next speaker, I would like to take this time to remind the audience who are watching from home that we have the audience choice poll, which is available with the link below. Next up, we have Emmanuel Diaz Mendoza. He's a Master of Science candidate in the Department of Civil Engineering and Applied Mechanics. His presentation today will be on from feces to the environment, the relation between organic matter and antibiotics resistance genes in wastewater. Thank you.
I want you all to do this, and I want you to imagine what if by doing this, we could all exchange genes among all of us. Now, if we had this ability, we would be able to change the color of our eyes or the color of our hair. Now, I want you to forget about these superfluous things, especially because I look awful in those colors. And if we had this ability, we would be able to change to cure genetic diseases. Now, unfortunately, we are not at the point of curing genetic diseases by exchanging genes. But what if I told you that there's one organism that is already doing it? And what if I told you that this organism is plotting against us? Now, bacteria do it, and they do it to combat our attack of antibiotics. This basically means that one little helpless bacterium can become superbacterium. Now, this is important because 23,000 people die from this kind of infections around the world each year. Now, I want you to think about where do bacteria go after they get excreted from our body. Well, they go to the sewers, then to a wastewater treatment plant, and then to environment. Now, sometimes they go directly from the sewers into the environment. Fortunately, we have a lot of research on the medical field. Unfortunately, not so many on how it spreads through the environment. Now, let me tell you about my research. My research deals with the relationship between organic matter and resistance genes in wastewater. And to study this phenomenon, I am running bioreactors to study, and then applying qPCR to study the abundance of these genes. We are testing 3 different conditions in which 2 of them are negative controls, 2 complex compositions in which 15 organic constituents and 17 inorganic constituents are added, and 3 replicates per each condition. Now, this would make a total of 18 reactors. This will help us better understand the dynamics between organic matter and resistance genes, especially in relationship to what bacteria use as a source of energy. This, in turn, will help us improve removal efficiency of these genes in wastewater treatment systems, which would create a basis for a legal framework on this emerging pollutant, which would prevent us from discharging these genes into the environment. Now, my research would help us take a step forward into stopping the threat of antibiotic resistance. Thank you.
Thank you, Emmanuel, for the very good presentations. And it's really surprising to know that bacteria have such superpower. And fortunately, we have research in this area to combat the sustainability of the wastewater treatment. Next up, we have Noah LeFrancois. He is a Master of Science candidate in Mechanical Engineering. His presentation today is how your table salt can decarbonize our power grids. Thank you.
Renewables like solar and wind are plentiful, but they only produce power while the sun is shining or the wind is blowing. This intermittency is a big obstacle to decarbonizing our grid. What we need is some sort of battery that can store surplus energy when we have it and convert that energy back to electricity to meet demand when production is low. Electrochemical batteries, like the one in your phone or your Tesla, contain expensive materials with a big environmental impact. But what if I told you that a sustainable solution to this problem could be found right in your kitchen? We can meet these energy storage needs using molten salt. Molten salt is just like the table salt found in your kitchen, but heated up to temperatures as high as 800 degrees Celsius so that it melts into a liquid. These temperatures are so high that the salt emits visible radiation and glows red hot. We can store energy as heat in big tanks of the salt and access it later when we need it. Salt is cheap and abundant with much lower environmental impact than electrochemical batteries. One of the things we need to understand is how heat flows through the salt. We understand heat transfer by convection at normal temperatures, like a boiling pot of water or the air in a heated room, very well already. But at the high temperatures that I'm working at, the thermal radiation emitted by the salt interacts with the convection in complicated ways that our usual heat transfer models don't predict very well. If we understand how heat flows through the salt, then we can design cheaper and more efficient thermal energy storage systems. I'm building an experiment to measure this heat transfer behavior in molten salt. Traditional methods for making these measurements rely on invasive techniques like sticking a probe inside of the liquid, which doesn't work very well for the hot and corrosive salts that I'm working with. Instead, I'm applying new techniques that rely entirely upon non-invasive optical measurements. I'm using a combination of laser imaging and infrared camera measurements to take high-speed videos and measure the heat transfer in a tank of molten salt. You can see here one of the first ever videos of molten salt produced using this technique. The yellow arrows show the measured velocity at each point in the flow evolving over time. The orange arrows show places where we measured anomalous velocities due to signal processing issues and replaced these outliers using a smoothing filter. While we've successfully demonstrated that this technique works in molten salt, our next steps involve quantifying the sources of uncertainty in our measurement, like this outlier smoothing and the accuracy of our heating conditions, so that they can be used to rigorously validate theoretical models. By the end of my project, I will have a fully calibrated measurement technique that can not only be used for high-quality heat transfer measurements in the experiment I showed you, but can be applied by researchers around the world to design the cheaper, safer, and more powerful molten salt thermal energy storage systems needed to power our sustainable future. Thank you.
Thank you, Noah, for the very good presentation. It's very good that we can use the salt, which is very inaccessible, to get our energy storage technology to be accessible to everyone, that we can have a sustainable future. Next up, we have Galih Suwito, who is a PhD candidate in the Department of Mining and Materials Engineering. His presentation today will be on creating an atomic Lego set of ground photonic materials on silicon for next generation internet. Thank you.
Explosive data growth has placed an enormous demand on the network, having 5 times more traffic occurring within the data centers compared to the total internet traffic. As we transfer more information, we are actually hitting more copper wire cables located inside the data centers. This makes a huge power consumption equivalent to the national electricity needs for most of the countries in the world. What is worse than that is that 43% of this power is used to cool the computers only. That is why the current data centers are nothing else but big buildings with a bunch of big computers with a lot of much bigger fans like this. But optics or photonics can alleviate that. We can connect computer chips inside the data centers using light, and light doesn't burn any power. These chips are based on silicon, which are similar materials used in our daily gadgets. To realize this, what we need is a complete Lego set of materials grown on silicon substrate. As an example, germanium on silicon as the receiver part of the network. The problem is when we grow germanium on silicon, which is commonly occurred in vertical direction, atomic imperfections are generated that looks like bunches of half loops inside the germanium layer. This degrades the performance of the later to be grown photodetectors. In the lab, we ask ourselves a question: can we make the very first half loop of this imperfection to get extended and make it reside at the interface between these two materials, other than creating another half loop, another one, and another one? The answer is yes. By using gold, we can actually make the germanium to grow in lateral direction, and this make the very first half loop of imperfection to get extended and reside at the interface between these two materials. This results in a region of germanium with a very high quality, as shown in the red box. This technique could be virtually used to realize any materials on silicon, and we hope that in the near future, we could complete our Lego collections of materials for the next generation data centers, making those cooling systems worth of hundreds of terawatts of electricity no longer necessary. Thank you very much for your attention.
Thank you, Galih, for the very good presentation. We know that heating in the computers and data centers are really wide issues, and it's good that you did research in that field to help us use our computers in more efficient way and more sustainable to the environment. And that concludes the presentation for today. So thank you for the students who gave us a really good presentation, and also thank you all to the audience we have today. I'll pass it back to Professor Bergthorsen, who will be introducing the judging committee's members for you, and he will be announcing the 2022 ChangeMakers for the SEDTalks event. Professor Bergthorsen.
Thank you, Yiwei, and thank you to all the students for your hard work in preparing your presentations and for sharing your inspiring research with us. We'll now move to announcing our 2022 ChangeMakers, and at this time I'd like to make a final call to the audience to vote for your favorite presentation for the Audience Choice Award. I'd now like to introduce our selection committee, who are tasked with selecting our 2022 ChangeMakers. The selection committee was composed of members from industry, academia, as well as past ChangeMakers. First member of the selection committee is Avram Goldman from Pratt & Whitney, Canada. Second is Professor Alan Elker from Bioengineering Department, Professor Jan Kupaszynski from Chemical Engineering, Jamie Summers from WSP, Elena Corella Puertas, who is our ChangeMaker last year in the 2020 event, and Professor Stephanie Loeb from Civil Engineering. Normally, when we hold this event in person, this would be the moment where the judges would meet to deliberate and the audience would mingle and enjoy some food and beverages. And though we hope that we can resume that portion of the SEDTalks experience soon, for the time being, the judges held their deliberations remotely. The discussion was comprehensive, and in order to come to their decision, the judges had to consider a multitude of factors. Not only the delivery of the talk, but also other factors such as the student's topic, its relevance to sustainability and to TIZED's mission, representation across the different departments and topic areas, not just in the current cycle, but also historically over the course of our SEDTalks program. And also considerations around equity, diversity, and inclusion. So after the selection committee's comprehensive review, I'm happy to announce that the judges selected the following students as the 2022 ChangeMakers, in no particular order. Valerie Lamenta, Anirban Kundu, and Galih Suwito. Congratulations, and we look forward to working with you in the 2022 ChangeMakers SEDTalks event. At this point, we'll now move to the Audience Choice Award while we wait for the final votes to roll in. And I'd like to take this opportunity to say a few words of thanks. First, I'd like to thank the students for their presentations. I'm sure everyone today has learned something new, and we wish you all the best as you complete your projects. On behalf of the presenters today, I'd like to extend a special thanks to our entire selection committee for their time and involvement in the event. Special thanks to the TIZED team and to McGill's Media Services for their efforts in helping organize and coordinate this event. Thank you to the skill set staff at Teaching and Learning Services here at McGill, who offered customized support and training programs to all of our students working on developing professional and communication skills. I would especially like to acknowledge the important efforts of Andrew Churchill, who led the fall workshops, as well as all of the volunteers for providing peer feedback, as well as Mr. Yiwei Fung for being our MC tonight. Finally, the work of TIZED would not be possible without the strong support from our donors and our industry partners. Thank you. So it looks like our audience choice voting has concluded. And just a reminder that our 2022 ChangeMakers are not eligible for the Audience Choice Award. So for all of you watching at home, keep that in mind as I announce the results. So thanks to everyone who voted, and it looks like Noah LeFrancois is our winner. Congratulations, Noah. That concludes our event. On behalf of TiZed, I thank each and every one of you for being part of our SED180 event today, and we hope you can all join us in the spring for the SEDTalks event, where we'll have a chance to see the 2022 ChangeMakers present a more comprehensive talk on their research. If you're a graduate student in the faculty and are interested in participating in the training next year, please visit www.mcgill.ca/TiZed for more information, or feel free to contact TiZed@mcgill.ca. Thank you, everyone. Stay safe and happy holidays from TiZed.